Hello students, in the last session we saw projectile motion on a horizontal surface and on an inclined plane. Okay, so in this session we will do uniform circular motion and a small part which is like kinematic equation that is related to uniform circular motion. Okay, so this session will be one of the shortest session, so it will take around like 20-25 minutes. That's it, right? Okay, so we'll see what is meant by uniform circular motion, right? As the name suggests, uniform actually mean the object is moving with a constant speed. Okay, so obviously velocity will be changing because the direction is changing for a circular motion, right? So the velocity will change, but the thing is it is moving with a constant speed, which means, let's make it this way, the speed of the object is like 5 meter per second, which means it covers like every 5 meters. I mean it covers 5 meters in every 1 second. Fine. So in the situation, velocity will be changing, but the thing is, it is moving with a constant speed. Therefore, it is called as uniform circular motion, right? If it was like non-uniform circular motion, then the velocity, then the speed is also changing, right? So the speed is actually increasing. It is increasing from 5 to 6, 7, 8, something like that, or else the speed might be decreasing. Whatever it is, that is like non-uniform circular motion. But here they have but here they have given you it is like uniform circular motion, right? So for this uniform circular motion, what should be the centripetal acceleration or acceleration that is involving in this motion? That's what we are supposed to find here. So whenever an object is moving in a circular path, you need an acceleration. Okay, so that acceleration is called a centripetal acceleration. Let's see in which direction the acceleration is acting and what is the magnitude of the acceleration. Okay, so that's what we are supposed to find here. So in the situation, I've considered an object. Fine. So let me consider this to be the initial position, and this will be the final position. Okay, it is moving in a circular path. Okay, the distance it has covered in the periphery will be like del r. Okay, the radius here is like r, and the angle it has swept is like theta. Okay, so these are the given things. Fine. So what I need to find here is the acceleration. Fine. Obviously, the velocity is changing. So to get the acceleration, what will be the formula? So to get the acceleration, the formula actually is del v divided by del t, which means I'll substitute v final, vector v final minus vector v initial divided by the time interval, which is like del t, right? So that gives me the acceleration a, right? So if I need to get the direction of the acceleration, it is nothing but the direction of change in velocity gives me the direction of the acceleration, right? Because obviously time isn't direction oriented, therefore direction of the velocity, change in velocity gives me the direction of the acceleration. Fine. So to get the direction of the acceleration, I'll have to subtract final velocity minus the initial velocity, right? So let me draw the triangle, okay, such that final velocity minus initial velocity. Let me consider those two vectors. So here initial velocity, final velocity is this one, okay, which is at certain inclination. I'll put that one. Got it? So the final velocity here is like in this direction, which will be like vf. Okay, vector vf will be the final velocity, and then negative of initial velocity. Okay, so minus of initial velocity. So this was my initial velocity. Negative of initial velocity will be flipped, so it will actually be downwards. Okay, so you will have minus vf, which will be acting downwards, minus vi, which is like downwards. In both those situations, I've just mentioned vf and then vi to make sure that you know this is like final and this is like initial, but we know that the magnitude of those velocities are just the same thing, right? Because this is an uniform circular motion. Okay, so this will be like final and this will be like initial. Okay, so what should be like del v? Del v is nothing but vf minus vi. So here to get the del v, this will be my resultant vector, vector r. Vector r is nothing but del v, which is nothing but the subtraction of vector subtraction of vf minus vi. Therefore, to get the del v, I'll have to start from the origin. Okay, so this is something that we have seen in the first session of this chapter. Okay, so I'll consider this to be my starting point and the final will be this position. Okay, so this gives me change in velocity, which is like del v in this situation. Got it? So if you look at this thing, it is pretty clear del v is actually directed towards the center. Okay, if you draw this diagram slightly above and then if you just consider, then in this that will be pretty much similar, such that del v will always be directed towards the center, which means like origin. Okay, so we just take these two interval as close as possible and then draw a diagram draw an final minus initial velocity vector to it, the del v vector will always be directed towards the origin, which means it will always be directed towards the center. Fine. So in this situation, it becomes clear you are having an acceleration. That acceleration is directed towards the center. Fine. You might have felt it when you are swinging in as an object. Okay, in that situation, you know that at every instant you will be pulling the object towards the inside. Okay, so that inward pull is nothing but the inward acceleration that I'm giving over here, which is called a centripetal acceleration here, right? Fine. So now I have got the del v, which is the centripetal, which gives me the direction of the centripetal acceleration. So the direction of the centripetal acceleration is actually acting inwards. Fine. So now I'll have to find the magnitude of centripetal acceleration. So to get the magnitude of centripetal acceleration, I'm just going to compare these two triangles. Okay, so when you compare these two triangles, okay, so these are like geometrical stuff. Okay, so these two triangles are actually a symmetric triangle. Fine. So you just take a uh, take a sheet and then draw the circle and then consider these radius and then put a triangle. Okay, same way you just draw a perpendicular line. Fine. So at every instant, the velocity of that object is going to be perpendicular to that of this radius. Okay, so that's how it's going to be, because it is going to move outwards and the radius is going to be perpendicular to it. Therefore the velocity will be perpendicular to this radius, and in this instant also the velocity will be perpendicular to that r vector. Okay, so you just combine these two velocities in this fashion and then get two triangles. Okay, when you compare these two triangles, obviously these two triangles will be like a similar triangle. Okay, so these are just a geometrical stuff. Therefore it becomes clear that the triangle, let me put pqr, so the triangle pq and then r, and in the situation, if I just consider it, if I just rotate it in this fashion and then insert it, I'll get this triangle, right? So here you got this to be like p dash, q dash, and then r dash. Fine. So these two triangles are obviously a similar triangle. Fine. So if it was a similar triangle, I'll be able to consider the sides, right? So here if I consider the sides, it will look something like this. You will have del v divided by v. Okay, so you'll have del v divided by v for p dash q dash r dash triangle, which will be equal to del r divided by r in the triangle pqr. Okay, so you'll have del r divided by r. Fine. So now I have got the relation between these two triangles. Fine. So the thing that you need to know is these two triangles are actually similar triangle. That's why I'm able to relate this stuff. If you have to verify whether it is a similar triangle, then you'll have to draw this entire diagram using compass, and then you get these two triangles. Fine. Then you try to match it. Those two sides will actually be similar to each other. Therefore this is actually a similar triangle. That's the only way how you could figure out these two triangles are similar. Fine. So these are some geometric stuff. Fine. So you ended up getting del v by v, which is equal to del r by r. Now you do the rearrangement thing so that we can find the acceleration. Okay, magnitude of centripetal acceleration. So del v, I'm just going to do the rearrangement thing such that you will have del v divided by del r, which is equal to v divided by r. Okay, so to get acceleration, I'll have to have del v divided by del t. So what I'm going to do is I'm just going to divide del t on both those sides. Fine. So if I divide del t by both those sides, I'll end up getting the centripetal acceleration. Fine. So we'll have del v divided by del r into 1 divided by del t, which is equal to v divided by r into 1 divided by del t. Okay. So now what I'm about to do is I'll consider this term del v by del t as acceleration, because change in velocity divided by time will give me the acceleration. If the limit was so small, then I'll be able to replace this one as dv by dt, right? So you will have something like this. Let's do a differential thing into it. So you'll have dv by dt, which is nothing but a instantaneous. That's what I've written over here, into 1 divided by dr, which is equal to v by r into 1 divided by dt, right? So now if I do a little bit rearrangement, then I'll get the instantaneous. Okay, so here this entire term could be considered as a instantaneous. Dv by dt will be like a instantaneous. Then if I do the rearrangement on the right hand side, you will have v by r into dr divided by dt, right? Got it? So now I have got VBR into dr divided by dt. I'll consider this dr by dt as my velocity, right? So change in displacement divided by time will give me the velocity, right? So dr will be this small change divided by the time interval will give me the velocity in that particular instant. So that will be the instantaneous velocity at that point. The velocity here is actually the same magnitude, right? Therefore I'll replace this one as v. Okay, so I'll replace that one as v. So we'll end up getting two v's on the numerator and then one r in the denominator. Therefore, centripetal acceleration AC will be equal to v square divided by r. Right now, I have found the magnitude of the centripetal acceleration. Already, we know that the acceleration is directed towards the origin, which means to the center in this case. The thing is, the magnitude of that centripetal acceleration will be equal to v square divided by r. That's what we have found over here, right? You should be clear with this one. So to get this centripetal acceleration, what we did is we just took two similar triangles. Okay, so one triangle was with respect to velocity and the other one was with respect to the displacement. Okay, so I just matched those two triangles and then I just shrunk it to a differential element. When I shrunk into a differential element, I got the centripetal acceleration at that every instant. Okay, so that instantaneous acceleration is nothing but the centripetal acceleration, which was equal to v square divided by r. Fine. Now we will see angular velocity and then the angular acceleration. Fine. So this is something that you could match directly with the velocity and acceleration that we have already learned. Okay. We know that velocity and acceleration are vector quantity. Same way, angular velocity and angular acceleration is also vector quantity. But as if now, we'll just learn it like a scalar quantity. Okay. So we will introduce vector into it while learning the chapter systems of particles and rotational motion. Okay. So that is like couple of chapter ahead. While doing that chapter, we will learn how to introduce vector into this angular velocity and angular acceleration. As if now, we'll just find an overall understanding. How should the magnitude be related? That's what we're going to see now. Okay. So angular velocity is something like directly derived, directly understandable from the velocity itself. In velocity, we know velocity is nothing but change in displacement divided by time interval. Therefore, here it is nothing but the change in the angle divided by the time interval. Okay, so the notation that we use for angular velocity is omega. Therefore, here for omega, I'll have like del theta divided by del t. That gives me the angular velocity. Okay, simple, straight away. Then, if it was like a complete rotation, then complete rotation should actually be 2 pi, right? Okay, divided by the total time taken to complete one cycle or one circle in this situation. Therefore, here that will be like time period capital T. Fine. Whenever one cycle is completed, I'll call that one as time period. Fine. So the time taken to complete one cycle is called as time period. So that is why I've written here it is like capital T. Okay, so that's what I've written over here. Time taken to complete one revolution or one cycle is called as time period. So if it was like one complete cycle, then I could actually match it with 2 pi, right? So omega instantaneous will be like differential element of theta and time. Therefore, it will be like d theta divided by dt. Okay, so these are something that you need to know regarding angular velocity. There are more to it. How we'll do all those things in upcoming chapters. Okay, as if now you just need to know angular velocity is nothing but change in theta divided by the time interval. Okay, so next you have got the angular acceleration. So obviously angular acceleration should be like change in angular velocity divided by the time interval. Okay, so alpha will be equal to change in omega, right? So the symbol for angular acceleration is alpha. Therefore, alpha, which is equal to change in omega divided by change in time interval, right? Okay, so you should be clear with angular velocity and then the angular acceleration. We are almost into the last part of the session, which is relation between linear velocity and angular velocity. Okay, now I'm going to relate between linear and then the angular velocity. Okay, so we know that linear velocity is nothing but what is the distance that it has traveled in this arc, which is like ds divided by dt. That gives me the linear velocity. Now I'll have to relate this v with respect to omega. Okay, so to to do that relation, we know that omega, which is nothing but d theta divided by dt, right? So d theta is the small theta that is swept in this case, fine. So how should I relate between theta and ds? So this is like a direct relation that we have learned in the first chapter, okay, units and measurements chapter, where d, in order to get the theta, I'll just divide the curvy length divided by the radius. So ds here will be equal to ds here, I mean d theta here will be equal to ds divided by r. Okay, so that gives me d theta, right? So what I need over here is ds, right? So if I do the rearrangement, you will have r with, you will have ds which is equal to r d theta, ds which is nothing but r d theta, right? If I substitute this one in the above equation, instead of ds, if I substitute that one, you will have v which is nothing but, you'll have v which is nothing but r d theta divided by dt. Okay, so now I have got v which is equal to r d theta divided by dt. So this d theta could be replaced as omega, right? So if I do the rearrangement thing, I will have v which is equal to r d theta by dt. Instead of d theta by dt, I'll substitute like omega, right? So the equation that I've got over here is v equals r omega. So the tangential or linear velocity will be related with angular velocity with r. Okay, so the answer here is v which is equal to r omega, right? So that's the relation that you need to know. So this thing also has vector notations into it. We'll do that one in upcoming chapter. As if now what you need to know is v which is equal to r omega, right? So we will introduce cross product, dot product, and all those things, right? So when we introduce those concepts, we'll get to know how to relate it vectorially. As if now what you need to know is v linear velocity, v will be equal to r omega, right? So this is the relation between linear and then the angular velocity. Just one more part is left. We'll do it in the next page, right? Now we will see kinematic equation for circular motion. Okay, so here I'll do the relation between the kinematic equation that we have already learnt with that of the circular thing. Okay, for circular motion, we'll consider angular acceleration to be like alpha, and then velocity to be like angular velocity, okay, which is like omega, right? So obviously this is not an uniform circular motion because you are having alpha into it, which means the angular velocities keep on changing. Okay, so if angular velocity is changing, then in that situation you will have like change in velocity, right? So obviously this is not an uniform circular motion. This is actually a non-uniform circular motion which has constant angular acceleration. Okay, so here the angular acceleration is actually alpha, right? So let me do the relation between the circular one and then the normal linear equation. Got it? Normal linear motion equation. Okay, so here you have v equals u plus at. So instead of v, I'll substitute like omega. Okay, so omega, that will be my final velocity, which is equal to the initial angular velocity, which is like omega naught, plus instead of a, I'll substitute like alpha t, right? So this is just the direct matching between the linear kinematic equation and then the circular thing for the kinematic equation. Okay, so the way I match is because all those things are just the same, right? So if you have an angular acceleration, then obviously angular velocity is going to increase, right? Same way over there, you had an acceleration. With respect to that acceleration, the velocity was changing, right? So here I'm just matching it with the angular acceleration. I didn't match it with the centripetal acceleration because I got centripetal acceleration for the change in velocities, right? So that was the direct application of the linear velocity. Okay, but in this situation I'm comparing it with the circular thing. Okay, so with respect to the circular one, you got like angular velocity, and the same way you got like angular acceleration. I'm just comparing that with the rotational motion. That's what I'm doing over here. Okay, so you should be clear with this thing that I'm telling you. Okay, so you got like omega, which is equal to omega naught plus alpha t. So the initial velocity was like omega naught and the final angular velocity was like omega. Okay, so then you have got like theta, which is equal to omega naught t plus half alpha t square. Okay, so that's the kinematic equation for rotation. Then you have got v square minus u square, which is equal to 2as. So if I replace with rotational component, you'll have like omega square minus omega naught square, which is equal to 2 alpha theta. Okay, so now you should know the kinematic equation for the rotational motion, right? So it is just the direct relation between the kinematic equation that you've already learnt with respect to the linear motion. I'm just matching it with the rotational motion. That's it, fine. So no doubt should be there with respect to this kinematic equation. Then you have some extra little bit thing that you need to know regarding non-uniform circular motion, right? So when you have got non-uniform circular motion, what actually happening is the the magnitude of velocity is also increasing, which means you are having tangential acceleration. That is when you will have the velocity to be increasing, right? So only when you have the velocity to be increasing, only when you have velocity to be changing, at that instant you will end up having angular acceleration, right? If the velocity is just constant, which means speed is constant, then you won't have angular acceleration. In that situation, angular acceleration alpha will be equal to 0. Okay, so this thing doesn't comes into picture. Okay, so whatever instant you take, omega will be the same, right? So to get the theta, just multiply omega and then the t, you'll end up getting the theta. Okay, so to use this formula, it should be a non-uniform circular motion with constant acceleration. Okay, angular acceleration, right? So if that was the case here, then obviously you'll have tangential acceleration into that object, which means the velocity is increasing in the circular path. Same way it is also moving in a circular path. Okay, so in that situation, what will happen is you are having a tangential acceleration, which is called as a tangential. Okay, so you will have a tangential. Same way, you will also have an acceleration that is directed towards the center. Okay, so to keep that object in a circular path, I always need to give a centripetal acceleration which will be directed towards the center. So you are having a centripetal acceleration. Okay, so there are like these two acceleration. So the net acceleration will be the vector addition of tangential acceleration and then the centripetal acceleration, right? Therefore, the net acceleration here in the situation will be the vector addition of tangential and then the centripetal. Okay, so vector addition here is nothing but these two things, right? You just take one vector and place it on the head of the other one, you'll end up getting the a net, right? So it seems to be like an right angle triangle straight away, right? This is like a 90-degree step. Therefore a net will be equal to the Pythagoras theorem, right? Which will be like root of ac square plus ad square. Okay, so a net was equal to root of ac square plus ad square. Okay, so that will give me the a net. Fine. So you should know the difference between centripetal acceleration and then the angular acceleration. These two things are not the same thing. Okay, centripetal acceleration is something that you got from the linear motion itself. Okay, with respect to that velocity, I just did all those differentiation, and then small relation got me the centripetal acceleration. So you should always give that inward pull. So that is responsible for that centripetal acceleration for the object to move in a circular path. Okay, if you didn't give that pull, what will happen is it will just move in that straight path. Okay, if there wasn't any centripetal acceleration, it will just move with that constant velocity. As you keep on pulling it inwards, the object was moving in a circular path. So to get that inward pull, I just found like centripetal acceleration. The topics that we saw in this session were like uniform circular motion. In uniform circular motion, we saw like what is meant by centripetal acceleration and the magnitude of centripetal acceleration. Okay, then we saw angular velocity, angular acceleration, and then we saw relation between angular velocity and then the velocity, linear velocity or tangential velocity. Okay, then finally we found like relation between kinematic equation of linear motion and then the circular motion, right? Okay, so then we saw like non-uniform circular motion, some basic things, right? So these are something that we have seen in this part. Okay, so with this, all those theory part that are related to motion in a plane got completed. Fine, so in the next sessions we'll be doing PVQs. Fine, so with this the video gets completed. Bye.